Hey, nice to see you again. I was a little worried that maybe the last topic was too much, but I'm glad to see that I have a brave audience. Okay, this time we really are talking about numbers. In particular, the properties that they hold. Now, I've already said how sets are a fundamental idea of mathematics, but there's another equally fundamental concept that we need to talk about, and that is the idea of axioms. So, I in my first video I defined what mathematics is, which is, you know, using true statements to figure out more true statements. But okay, so you have statements that depend on the truthfulness of previous statements. Maybe these previous statements also depend on something even more primal, right? Well, it's got to come to a stop, right? Eventually, every statement has to be based on just some piece of knowledge that is just true without being able to prove that they're true. Well, that more or less is what an axiom is. It's a true statement that it's so primitive that it cannot be proven with a previous piece of knowledge. And you might be thinking, well, if we can't prove that this statement is true, why would we take it as such? Well, all axioms are based on a true phenomenon. You're not just gonna make something that's clearly incorrect an axiom. You're gonna see something that you know is true, but it's just so elemental that you have no other option to just say, well, it's true, or at least to say that I'm going to assume that it's true, and we'll see what happens. So that's what I want to talk about today: the axioms of real numbers. Oh, and by the way, remember that strange mathematical language I told you about? Well, I'm gonna kind of give you almost all of it, if not all of it, because it's just easier to write. You can make something that will be a long sentence into a short statement. So you're gonna have to suffer through it. Sorry about that. Okay, so today we're gonna talk about real number axioms. But before we get to that, right, let me show you this weird language. Well, this one we already saw. It's like whatever you want to call that, right? And it means belongs to or it's an element of, right? So belongs to is an element of, or just in, right? So for example, if I say a is an element of the integers, right? Well, I'm saying that a is in the integers. It belongs to is an element of, so on and so forth, right? All right. This upside down capital letter A is gonna mean for all, or for each, for every. So how do you use the symbol? You say, okay, for all elements in the integers. Let's say that, right? So here I'm just saying, I'm just saying here that this element belongs in integers. But if here I'm saying that for all elements that belong in the integers, and then something should follow. Okay. Well, here's another one. This another capital letter that's kind of backwards, right? This one just means there exists. There exists. So let's say if I say for all a in the integers, comma, there exists a b in the integers, and then we're gonna add more to that. Now, in some special occasions, not only does something exist, but it's the only type of its kind. So we say there exists unique. We just add a exclamation mark next to the exist symbol. So, but that's all it means. There exists unique. So again, right? Maybe we're saying for all elements of the integers, or for each element in the integers, there exists a unique element in the integers, such that maybe something happens. Well, I keep saying such that, right? So here's the last one. Now, technically, sometimes some people just do again a reflected this symbol, and it just looks like that. Other people do make sure that it has this little extra thing, but either way, it just means so that, or such that. And we can say for every element in the integers, there exists a unique element in the integers, such that a plus b equals 0, for example, you know. So again, I think a big reason why we use this language is so that we can compress big sentences into this type of small statements, right? There's actually a very interesting connection between the for all and there exists. We won't talk about it today. This is all the vocabulary that we need from now on. Okay, so the axioms of the real numbers. So basically, these are rules that apply to real numbers, and that's it. It just, we don't really can't explain why they're true. We just know that they're true, and we can't really prove why they're true. So we just believe that they're true. That's what an axiom is. Okay, so let's start with the first one. So axioms. So for any two real numbers, so for any or for all a, b in the real numbers, well, we're just gonna say that a plus b is also gonna be a real number, right? So again, I mean, think about it. How would you even prove this statement to begin with, right? If you have two real numbers and you add them, you get another real number. I mean, you might look at that and think, well, duh, right? But like proving that, well, how do you do that, right? So instead, we just make that an axiom. Maybe you can think of axioms as, oh, so obvious, or that they're true. Not all of them. I mean, I'm going to expand here. Moreover, if A equals C and B equals D, then A plus B equals C plus D. So they're kind of saying, okay, if A is equals C, B equals to D, right? If I add this two, then it should be equal to adding this other two, right? Again, maybe you might be saying the a lot of the times, but that's what axioms are, right? But okay, now we're guaranteed that anytime you add two real numbers, you will get a real number. Okay. Another interesting fact about real numbers: for any a, b in the real numbers, so no matter which two real numbers you pick, a plus b equals b plus a. Right? 3 plus 5 equals 5 plus 3. But again, you know, again, look, okay, maybe this shows the point of why it's not such a duh, right? I mean, pi is a really interesting number, right? And it's irrational. It never ends. So pi is a real number. Now there's another interesting number that also is irrational. It's actually equally as cool as pi, which we call e. Right? It's 2.818. Blah blah blah. So again, this thing is an infinite. It's an infinite decimal. This thing is an infinite decimal. So how do you know that pi plus e is also a real number? How would you know that? I mean, I did say on the last video that a real number just corresponds to some type of distance, right? So you can say, okay, pi is a certain distance and e is a certain distance. So if you put those two distances together, you get whatever that distance that you get is pi plus e, and that's the end of that. Yeah, I mean, but again, now we're looking at like something beyond the physical world, and you know, without a physical world, yeah, pi plus e is still a real number. Again, all right, let's move on. I'm just saying, it's not as duh as you might think, but anyways. Okay, all right. Now for any a, b, and c that are real numbers, a plus b plus c equals a plus b plus c. So, okay, maybe we haven't talked about parentheses that much. This is barely the third video I've made, right? So, but I mean, the way that you read this is that, so if you add two numbers and then you add the third one, you should get the same result as if you would have added the last two and then added the first one. This is the associative law. So again, now you know that it's something that we are allowed to do. Okay. Number 4. The real numbers contains a unique element. So there exists a unique element 0 in the real numbers, such that. So again, I can I could use this symbol right here, but I can also just write such that s dot t dot, right? So there exists a unique 0 in the real number such that a plus 0 equals a for any real number. Alright, so there exists a unique element that we're going to call 0 such that when you add it to any real number you get the same thing, right? So if you notice, so far the first 4 axioms are all about addition, right? So then maybe let's start getting into multiplication. Well, let's try to make the same things here, but the multiplication version, right? For every a, b in the real numbers, a times b is also a real number. So again, pi is a real number and e is a real number, so pi times e should also be a real number, right? Moreover, well, if a equals c and b equals d, then a times b should equal c times d. So again, same thing, kind of like a substitution, right? So these two, the first axiom and the fifth axiom, kind of tell you, yeah, you're allowed to substitute some things if they're equal. Okay, well, what will be axiom number 6? Well, if I'm gonna keep copying this, right? I just noticed that I skipped one. But if I'm gonna keep copying this, so if I multiply them, a times b should be equal to b times a. So again, 3 times 5 should be equal to 5 times 3. So this goes with this one. This goes with this one. So then now this one, this is the next one, right? For every A, B, and C in the real numbers, if you multiply A times B and then multiply C together, is the same thing as if we multiplied A to B times C. And then on this one, right, we said, okay, there's an element so that when you add it, it doesn't do anything, right? So on the next one, there exists a unique element we're going to call 1 in the real numbers, such that 1 times A equals A for any real number A. And then people like to add this distinction. By the way, this element 1 is different from the element 0. Okay, well, again, so here's the one that I forgot, right? For any element in the real numbers, there exists a unique element also in the real numbers, such that A plus B equals 0. In this case, we say that B is negative A, basically. So we call this, so the fact that we say that it's unique is actually a big deal. That's why we get to say, well, it's not only is there some unique, that for each element A, there's a unique element B that adds it up to 0, right? Because it's unique, we can straight up say, well, actually, we're just going to call this guy specifically negative A. And the multiplication version of that is, for any real number, there exists a unique other real number, such that A times B equals 1. Same thing. In this case, we say that B equals A inverse. So sometimes when you see a negative 1 as a power, it just means inverse, multiplicative inverse. But this one is kind of special, right? So we also denote it as 1 over A. Okay. Well, we have 10 so far, but we need one more. One that's very important. For any A, B, and C that are real numbers, comma, A times B plus C equals A times B plus A times C. So the distributor property, right? It's actually an axiom. And I mean, I don't know, just as a, you know, why should, so I mean, all these axioms are based in reality, right? This one in particular is kind of easy to explain. I mean, some are easier to explain than others, but if you had a rectangle, so you probably maybe learned that, you know, multiplication is not just counting, as you know, as I said in the last video, but it also has to do with area, right? So if you had a rectangle where the length of the triangle, the length of the rectangle is, let's say that this length is A, from here to here is, well, from here to here is B, and then let's say that this length from here to here is C, and then the width is length A. Well, are we saying that if you multiply A times B plus C, well, you know, you're gonna have one rectangle of area AB and another rectangle of area AC. So, you know, one thing that I do tell my students is that, you know, anytime if that you feel like you're struggling with this, there really is no shame in going back and maybe drawing a picture of area, right? So again, this kind of relates to a rectangle with one side being length A, but then the other side being a combination of length B and length C. And as you can see, right, this part's going to have area A times B. This area is going to have area A times C. So in total, A times B plus C should equal AB plus AC. Okay. So these are the 10 axioms of the real numbers. Now, maybe there's a true statement in mathematics that you don't see here, right? Well, these axioms are going to be the building block for us to come up with new statements. So, for example, on the first video, you do algebra, right? And when you solve for algebra, what do you end up doing most of the time? Most of the time, you end up adding the same thing to both sides, right? Multiplying the same thing to both sides. Well, now we can just prove these statements. So, let's see. So a statement, let's say, if two quantities are equal, if A equals B, then adding the same thing to both sides makes them still equal. Then A plus C equals B plus C. Right? So that's our statement. Well, how would you go about proving this, right? Well, the only thing we know is what the assumption that they give us, right? So we know A equals B, right? And then here's an idea. Call me crazy, but also, C equals C. I mean, maybe we should have. I mean, sometimes maybe we shouldn't think too hard about this, right? I guess it wasn't really stated in anywhere that it's an axiom that any number equals itself. But then let's just take it as such, no? But if you do agree with me that any number should equal itself, well, now we know two things. We know that A equals B, and we know that C equals C, right? So then, according to the very first axiom, that if two numbers are equal, and then two numbers are equal, right? If you add both of the left-hand sides, it should still be equal to adding both of the right-hand sides. That's what the axiom is saying. Again, the axiom is saying that if this is equal to that and that's equal to that, then if you add the left-hand sides, A plus B, it should still be equal to adding the right-hand sides, C plus D. So here my proof, okay, if I know that A equals B, and if I know that C equals C, then by axiom 1, let's say, we know that the left-hand side with the left-hand side, A plus C equals B plus C. And that's what we wanted to get at, right? This is the endpoint that we wanted. That's it. I would say we proved it. So yeah, I mean, if you're looking at the statement, if A equals B, then A plus C equals B plus C. And you might be thinking, again, duh, right? But unlike this other 11 statements, this is a statement that we can prove. So it's not too obvious, right? I mean, if you don't think about how C equals itself, how would you go about proving A plus C equals B plus C? I don't know, that's just a food for thought, right? Should we really do the statement if A equals B, then A minus C equals B minus C, right? Well, okay, let's write this down. So what about statement if A equals B, then A minus C should still be equal to B minus C, right? So the truth is that none of these axioms really talk about negative numbers. If anything, the only time negative number comes up was with the additive inverse, which again, kind of wrote them the way that I wrote them. We will call them axiom 9, which says that any number has an additive inverse that we just call it the negative, right? So what I'm saying is that this first statement, if A equals B, then A plus C equals B plus C, I would say we proved that for all real numbers C. So maybe I should have added that. For any C that's a real number. Well, if I prove that for all real numbers, then I prove that for positive numbers and negative numbers. So the way that I would handle this is, how would I prove this? Well, I would prove it. I would handle it this way, I suppose. You just have to know. You just have to accept that maybe, for example, that A minus C, as long as you can accept that A minus C is equal to A plus negative C, then that's really all you need, because our statement would go as follows. So this is what we need. If A equals B, then, like I said, I just proved that I can add anything to both sides. So if A equals B, then A plus negative C should still be equal to B plus negative C. And then again, if you feel comfortable making this assertion, then that's all you need, right? Because if A plus negative C equals B plus negative C, then you're really saying that A minus C equals B minus C. So the point I'm trying to make is that, so yeah, you might see a lot of statements that we prove them for positive numbers, or we prove it for addition, and you might think, well, how come we didn't prove it for subtraction? Well, because we don't need to. You know what? In fact, I'm willing to say, it's about time we throw this minus sign to the trash. And if you so if you see something like 7 minus 5, you should see the statement 7 minus 5 as maybe 7 plus negative 5. And if you see it that way, well, like I said, now you have a bunch of axioms and even a new statement that deals with plus signs, not negative signs. So, well, let's see. Can we prove this statement then? Or do you guys even want to, right? That A minus C, A subtract C, just really equals A plus negative C. So again, nothing that we've seen so far really talks about the subtraction sign, right? So the only way that I can even maybe hope to prove this statement is the following. So what am I going to do here, right? Here's how I would say that I'm trying to prove it, right? So A minus C, let's look at that, right? So it's a number minus a different number, right? So again, again, the first axiom we talked about says that if you have two real numbers, then their addition is a real number. Well, have we ever agreed that if you have a real number minus another real number, you have a real number? So let's just say that's true. If it's really a duh, right? A number minus a number is a number. Okay, so say let x be this number a minus c, right? Assuming you're okay with me assuming that, right? Now here's another thing that I'm gonna maybe argue with you guys, right? So if x is a minus c, would you guys agree that if I add c on the right side, on the right hand side, then I have a? So for example, so suppose I add c to both sides, right? X plus c equals a minus c plus c. Again, here's where like we might just be arguing semantics, the axiom about negative numbers. So there is an axiom that talks about negative numbers, right? But again, we don't really say subtraction, we say just negative sign, right? So we say that if a plus b is 0, then b must be negative a, so but over here we're not saying we have a plus a negative c, we have a minus c, right? We're just arguing semantics. But if you agree with me that, well, adding c should undo subtracting c, right? If you agree with that, then we can make the statement. If you can agree that a minus c plus c is just a, then it's just a, right? Okay, so far x plus c equals a. What am I going to do that? Well, again, if you allow me to make the statements that I made so far, then the rest I can do is very mathematical. Because if we have x plus c is a, x plus c is a, right? Well, the next step is this. Again, if this x plus c is one quantity and it equals a, then if I add the same thing to both sides, then they're still the same, right? Then if I add negative c to both sides, we have that x plus c plus a negative c equals an a plus a negative c. And over here, while over here was telling you, well, can you do you do me a solid and say and agree with me that a minus c plus c is a, right? Well, over here I don't need you to do me a solid. Over here I know that c plus minus c is 0, according to, again, axiom, what was it, 9, right? So whereas over here I was telling you, do you believe me that this is 0? And so far, maybe, hopefully, you agree with me. Over here, I don't need you to agree with me because that is an axiom. So what I'm saying is that if x minus c plus negative c equals a plus negative c, well, c plus negative c is going to add up to 0. So then x plus 0 equals a plus negative c. And of course, x plus 0, again, there's no argument, that's an axiom. Anything plus 0 is itself, right? So x itself equals a plus negative c. So what have I done so far? Well, I started with saying x equals a minus c, or a subtract c. I ended up saying that now x equals a plus negative c. So again, if x equals this, but x now equals that, then now we can say that this equals that. So we can say a minus c, or a subtract c, is the same thing as a plus negative c. again, I, well, maybe you might have said from the beginning. Well, yeah, uh, a minus c is a plus negative c. Well, again, we're just arguing semantics. Okay, well, maybe you're satisfied now that if a equals b, a plus c equals b plus c, which again, it means that if two quantities are equal, and if you add the same thing to both sides, that they'll still be equal, right? And like I was saying before, we don't really need to do the minus case if you just accept that the following, right? That well, you know, instead of saying I'm subtracting c from both sides, I'm just adding negative c to both sides. If you have that perspective, instead that there's really nothing else to prove. But if you really have a problem with, okay, I don't really believe this part, this is the best explanation I can give you here. Alright, there's a few more things I really want to do, even though I see that the video is kind of long now, right? Let's do another statement. Like I said, you guys, the other thing that you do in algebra is, yeah, if two quantities are equal, then if you multiply the same thing to both sides, that they're still equal. So c times a equals c times b for any c in the real numbers. Well, again, this one's connected with this one. How would you prove this statement? Well, over here we prove the other one with substitution, right? Because apparently that was the first axiom. Well, axiom number 5 is the one that lets you do substitution for multiplication. So the proof is again simple. Suppose that a equals b. Suppose we know that. Well, the trick is the same. Also, so again, c is still equal to c, right? Yeah, hopefully. Well, then again, it was the same proof as the other one, except that we're now quoting a different axiom, right? And then by axiom, well, which one was it? Axiom 5. If this is equal to that and it's equal to that, and if you multiply the left side with the left side, then the right side and the right side are also equal, right? If a equals c and b equals d, then a, b equals c, d. So again, if I multiply the left side with the left side, so a times c should be equal to b times c. Now I wrote c times a equals c times b, right? But okay, I mean, if you really feel like I haven't finished doing this proof, well, go back to axiom 6, which says that a times b equals b times a, right? So for example, again, if you're not satisfied at this point, just remember that a times c equals c times a by axiom 6. And then same thing, right? B times c equals c times b. So again, okay, so again, now you know a statement that if two quantities are equal, you can multiply the same thing to both sides, and then they should still be equal. Well, again, I don't know if you really want to argue about this one, but I would say that we don't need to prove it. But yeah, right? If a equals b, then if you divide by the same thing on both sides, then they're still the same, right? A over c equals b over c for any c in the real number, just as long as it's not 0, because we can't divide by 0. The reason why I'm saying that there's really nothing to prove is because a over b, I mean a over c, right, is just equal to A times 1 over C. So, well, is it, I would say that proving this little thing is kind of the same thing as proving this other one, where like we're just really gonna be arguing about semantics. And just to clarify, right, why am I saying that? Okay, A over C. Well, you tell me this, is this not equal to A divided by C, right? So I think that has to be by definition, right? We really haven't talked about it, but that has to be what it is by definition, right? Well, but any number times 1 is itself, right? So what I'm saying is A is equal to A times 1, is it not? Yeah, maybe it's a combination of axioms, but it's true. So A divided by C would just be A times 1 divided by C. And would this be legal? If A times 1 divided by C, wouldn't this be the same thing as A times well, according to PEMDAS it's true, but I'm just asking. Times 1, but then divided by C. And then just to really make a point, if I put this parenthesis right here, right, because parenthesis means multiplication, so I have A times 1 divided by C. And if I have A times 1 divided by C, well, then I have A times 1 over C. Alright, well, the next video that I'll do is about fractions, I feel like, and hopefully this one will be short. Hopefully the video about fractions will be short, right? But again, what I'm saying is that this last statement that you can divide both sides, I'm saying that it's true if you can accept that A divided by C is just A times 1 over C. Because if you can't accept that, then that's what we did in the last thing again. If you have A equals B, then multiply 1 over C to both sides. Let me just write that to really clarify it. If A equals B, then multiply by the statement that we did prove, then A times 1 over C has to be equal to B times 1 over C. And this is how you get that A over C equals B over C. That's what I'm saying. I don't really want to go through like arguing semantics about why this is equal to that. This explains it all. That if A equals B, then you should be able to multiply 1 over C to both sides. So then 1 over C equals B over C, and then that should be the end of the discussion. Yeah. Well, actually, I'm not done with axioms. Maybe I need to do an axioms part 2. I'm going to do an axioms part 2. And then I'm going to do the video about fractions. Because fractions definitely deserve their own video. But, yeah, so let's just I guess we're just going to call this maybe real numbers part 1 or something. Don't forget to like and subscribe, comment, tell me if something wasn't clear. I can definitely answer any questions you have. So, yeah, let's leave it there. Thank you for watching.